In this video, we are going to delve a little deeper into our equations of motion for accelerated motion. I'm going to specifically tell you their derivations. This is just a fancy word to tell you where did these equations come from? How did they end up being linear? How did they end up being quadratic? How did these terms look the way they do? They were derived from something, and I'm going to go over the derivations with you now. So let's start with our first equation for motion, this linear equation here. Well, this equation comes from our velocity time graph for accelerated motion. So let's look at this situation where the object starts at an initial velocity and it is going to accelerate at a very specific rate, which is represented by the slope of this line, until it reaches some sort of final velocity up here. We have this graphical model, but we can use this graph to create a mathematical relationship to describe how the velocity changes with time. And that is going to come from this linear relationship here. Remember, this is the equation of a line, so we can represent it using y equals mx plus b. But again, y equals mx plus b is way too vague, so we have to start to customize it. So the first thing I'm going to do is replace my y variable with what the y-axis represents. That's going to be your final velocity, or just velocity in general. Next thing I'm going to do, x is too vague. Let's replace x with the x-axis, time. So now we just need to fill in what our slope and our y-intercept represents. So we already know that the slope of a velocity time graph represents the acceleration of the object. So we can replace the slope term with acceleration. The last thing we need to do is interpret our y-intercept. Well, the y-intercept is the velocity that the object starts at, its initial velocity. So we can plug in initial velocity for our b term. If you notice, now we have an equation that looks almost identical to this first acceleration equation. All we need to do is flip these two terms around, and we have this relationship here. Now, this is an equation, but it tells you a lot of things. It tells you that the final velocity that an object is going to move at, how fast it ends up moving, first of all, depends on how fast it's moving to begin with. That should make sense. If you're moving really slow to begin with, it's going to be different than if you're moving really fast. So your final velocity depends on the velocity you start at. It depends on how fast your velocity is changing. That is the acceleration. And it also depends on how much time you are letting the object accelerate for. And another way to interpret this equation is that the velocity you end up at is going to be equal to the velocity you start at plus how much your velocity changes. This acceleration times time term is really your change in velocity. So your final velocity is equal to your initial velocity plus all the velocity you gain or lose because of your acceleration. So yeah, know how to use this equation, but also know what else it is saying. So that is our linear equation. Now we have this second equation, which looks a lot more complicated. There is this quadratic relationship. It has three terms, and it might not be obvious where it comes from. So let's begin to break down this equation. This equation is describing the position you end up at, your final position. And it is saying it depends on three things. Your final position is going to depend on your initial position, where you start out. And then it's going to change. Your initial position is going to change depending on how fast you're moving to begin with. Your initial velocity, the fact that you're already moving for an amount of time, is going to cause you to gain some position. But because we are accelerating, your position is also going to change depending on how much you are accelerating, this rate of acceleration over time. All three of these displacements, the one caused by where you start, how much you gain just simply because you had an initial velocity, and how much you gain because of your acceleration, all three of these things together are going to determine your final position. Where you start, how much you gain just simply by moving, and how much you gain by speeding up. Now, this last term here, the 1/2 AT squared, it might not be obvious where this comes from, so I'm going to go through the derivation of this now. So from this same velocity time graph, we can come up with another relationship because we know that the area underneath this velocity time graph is going to represent the displacement delta x of this object. So if we want to know where this object ends up, we can use the displacement, and that's going to be the area underneath the curve, which is going to be this rectangle here plus this triangle here. Both of these two shapes are going to determine the displacement of the object. So if we want to calculate these areas, the area of this rectangle is going to be the base of it times the height. So if you remember, this point here where this graph starts represents the initial velocity of the object. So the base is going to be time and the height is going to be the initial velocity. So the area of this rectangle down here is the initial velocity of the object times time. Now we just have to find the area of this triangle. So the area of the triangle is going to be 1/2 base times height because it's a triangle. The base of this triangle is this time, t. So we've got 1/2 times time. The next thing we need to figure out is how high up does this triangle go? What is this length along this upper portion height? And this is a little more difficult to figure out. But if you remember, we already know the slope of this line represents the acceleration. The acceleration is the slope, so the acceleration is going to be rise over run, or h over t. If we were to calculate the slope, we would do the change in y, which is this height, over the change in x, which is the time. So if we want to solve for h, we can just multiply t to the other side, and we know h is going to be equal to the acceleration of the object times the time we let it accelerate for. So now we know what the height is. So the height we could plug in acceleration times time. So this is a little messy looking, so I'm just going to simplify this to 1/2. I'm going to pull the a over here. Now we have one time times another time. If you look at that, oh, this is where that 1/2 at squared comes from. So now we have this relationship for the displacement of the object is going to be equal to the area of the rectangle, which is initial velocity times time, plus the area of this triangle, 1/2 at squared. And this is almost to here. Last thing we need to do, the displacement of the object is equal to the final minus the initial position. And we can just add the initial position to the other side. And now we have all of these terms on the right side of our equation. We have our initial position plus our initial velocity times time. That was this rectangle here, plus 1/2 at squared. That was the area of this triangle right here. Anytime you're finding the area underneath this graph, you are actually always using this equation. You just didn't know it. But that is where this equation comes from. We get it by doing the area underneath this graph, and we get all three of these terms. Now, this equation version right here, the total displacement, is also a very useful version to memorize. Sometimes we care about initial and final position. Sometimes we care about these as two separate terms. But if we just want to know how far the object moves, its total displacement, if we don't care about its actual initial and final positions, I would use this version here. It just saves you a couple of steps. If I'm just asking directly about displacement, I would just move this term over to this side, this initial position, and just combine it to be delta x. So even though this equation version up here is not on your AP equation sheet, I would still memorize it. It's going to be very helpful. The last thing I want to point out is something really nice about this final equation. So we have this function of position in terms of time is equal to this whole part here. So if you look closely at this relationship, you can see that there is a quadratic relationship between position and time. Position is going to be proportional to time squared. That means that this relationship for accelerated motion between position and time is a quadratic relationship. And that is another reason why our position time graph ends up being this parabola. We have this relationship that is quadratic. Normally you see it in this form, y equals x squared, but we're going to see it in x equals t squared because we have position and time. But this quadratic relationship, the fact that this time term ends up being squared, is what causes all of these position time curves to be a parabola for accelerated motion.